Okay, so hello, I'm Merryn, and you didn't have the magic touch. Okay.
Evidently not.
I'm Merryn, this is Don. What we're doing is we're presenting some results from a larger study that we have been doing. All right, how do I make this go? Click. Click works. All right, so just give you a moment to read this quote. Okay, so in our study, we've been interviewing maths educators, and this was a quote from one of them. And this is sort of what we're talking about is sort of framed around this largely. Dawn.
So the team began with Merryn and I. This was an idea of Merryn's to build more into the literature of maths, of general education about the mathematician's view. So our team, just try to see from left to right. So Lorhelms Guzman, who's at UNSW, Jim Pettigrew, who may have gone to the other talk because he's probably heard this one 3 times. And Anthony Cronin from UCD, Gazam Intepe, who's at Western Sydney, Merryn, and myself. And as Merryn said, we've been interviewing maths educators from around the world. For this study, we were just looking at the first 33 educators that we'd spoken to. And there were a number of questions in our interviews, but the one that we're focusing on is what should students gain from their unit of study? In terms of the interviewees, you can see the distribution there. 5 of them were stats only, so statisticians. 18 were teaching maths only, and the rest taught both maths and statistics. That's back to you.
Okay, so we interviewed people. The people we were interviewing, we chose people who were practicing maths educators. So we didn't talk to theoreticians, and we didn't talk to people who had no interest in maths education. And we analysed the data using thematic analysis, using the approach described by Bron and Clark, which you can see on the screen. It's an iterative approach where you look through sort of line by line what each person said and assign a sort of a summary concept to it. You group the concepts, you put them together into themes, and you come up with sort of global groupings of what people thought.
So the themes that emerged from this were probably what everyone would expect. Content mastery, which broke into 2 sub-themes of technical mastery and conceptual understanding. Mathematical communication, which also broke into 2 sub-themes that we'll talk in a minute. Mathematical thinking and appreciation of mathematics, or mathematical appreciation.
So when we asked people, we kept the question as broad as possible. It was, what should your students gain from your unit of study? And these were very clear 4 themes that came out.
So, as I said, content mastery breaks into 2 areas. Technical mastery, which is the computational and procedural things, which to a lot of outsiders is what mathematics is. The fact that we can solve equations. I mean, I still get students in first year university saying, are we just going to be working on solving harder equations? Is that what maths is? And then conceptual understanding, which is probably more what we think about being mathematics, of understanding the concepts and the connections between them. These definitions are things both that came out of the discussion, but also that we've found back from the literature. Mathematical thinking, of course, is a very broad area, higher order, and comes in this sort of descriptions of higher order thinking, selections of methodologies, critical thinking skills, problem solving skills, understanding proof, critique of solutions, and you can probably add another 6 to that list of dot points. And then mathematical communication. 2, as I said, two dimensions: receptive language, being able to read mathematics. And I know Merryn and I were teaching a course at Western Sydney when I was there to Maths for Engineers preliminary, one of the things we found was that I'd give them some questions on that were hallucinations from ChatGPT or incorrect answers from class tests, typeset them so that they look good, and then ask students to critique them. And quite often they're not able to do that. They don't recognise good and bad mathematics when it's well set out. So that's an interesting point of how well do we teach that. And then the other half of that, of course, is expressive language. You have to be able to speak the language of mathematics in order to communicate with people. I was teaching engineers. They're not going to be mathematicians, but they'll have to be able to use the language of mathematics to communicate. And then the final one, maths appreciation, and this is probably the vaguest, but this idea of presence and relevance of mathematics, the social history, which Chauncey was just talking about, the beauty and interest of mathematics, the fact that it isn't just a lot of equations that have to be solved, and the interconnectedness between different areas of mathematics. So we felt, this is more our opinion, but we feel that there are sort of essential connections between some of these aspects and some which are certainly there, but not essential to an understanding of mathematics. So the white arrows are where we think there's an essential connection. So in order to understand content, you must be able to communicate. You have to be able to read the mathematics and speak it. And in order to be able to communicate, you have to have some understanding of the mathematics. So there's a two-way thing there. You can understand the content, but not necessarily be able to think mathematically. But in order to be able to think mathematically, you have to understand the content and so on. The mathematical thinking, mathematical appreciation thing, we don't have anything directly connecting there. We were sort of thinking along the lines of, to take an analogy, you can understand or you can appreciate, say, a Beethoven symphony without being a musician. So you can appreciate the music without actually thinking musically. Of course, if you think musically and you are a musician, you'll understand at a whole different level, but both things can happen. And the red arrow between computational skills and conceptual skills we'll talk a lot more about.
The one other thing to note here, it's sort of a side point, but in terms of what came out in the interviews of what we were teaching, we're really good at the content mastery stuff. That's a bit of a no-brainer because our job is to teach the content. There's also a very strong explicit focus on mathematical communication. A lot of people were describing precisely and explicitly how they were teaching their students to communicate. But we tend, as a whole statistically, and there's obviously exceptions, mathematical thinking, we tend to present mathematical thought as a given to students. Like Clemency was saying, we tend to, here's the theorem, here's the proof, here's the application, without showing them the way you think to get to that complete thought. And the same with appreciation of mathematics. There's sort of a general hope that the students will pick it up by osmosis, but in the interview, at least they're not things that we've been thinking about explicitly to articulate through our interviews.
And of course, the other problem with that is that the computational skills in today's framework, just about every problem that you can give students, they can put into ChatGPT and get the answer almost textbook perfectly. So what's the point of that? How should we then be teaching mathematics in that framework?
And so we come back to that original quote, which is, in this world of AI, when, your machine will do your maths for you, what's the point? What are we doing? We know that there's value in maths, but the general public and the lay public hold that mathematics equals computational skills. And we know that students sort of often come into uni expecting maths is computational skills, and they learn to turn the handle on things, and that's all good. We know that, hopefully we hopefully don't have to argue a case that communication, mathematical appreciation, mathematical thinking, and conceptual understanding are all valuable, no matter how much AI or machines or whatever you've got out there. They're things that have and hold their intrinsic value. The issue is this computational skills. What do we do about that? it's still part of maths. The fact that our students and the lay people sort of think that is maths is sort of the issue. So it's almost a bit of a PR sort of thing rather than a reality, because we've got a much richer reality that we see. So what we did was we dived in on this red arrow here and looked more deeply at this relationship between the computational skills and the conceptual understanding. And at this point, there was a difference between people who are teaching statistics and people who are teaching mathematics. Apologies to the statisticians in the room, but we've followed the maths path here. Statistics, if I generalise wildly, a lot of statistics teaching, that arrow is turning itself the other way around, and people are looking at the big picture and using machines to do the computation and focusing much more on the understanding. Mathematics is still much more the other way around. We teach, this is how you do a differentiation, this is how you do 5 different differentiations, this is how you use a chain rule, this is how you use, etc., etc. And the idea being that if you don't have any maths, you can't understand things. And if you're just looking big picture, if you're just looking up the conceptual understanding, well, you're not doing mathematics, you're being a lay reader. So you absolutely have to have the computational mastery. When there's no argument there about that. And certainly you need a basic amount of computational mastery. Firstly, because maths is a language and you need to be across the symbols enough to read the language. And secondly, you need to be fluent enough that you've got enough space in working memory to get to higher level things. There's no way you can read Dostoevsky if you're still sounding out your letters. And it's the same with mathematics. You need that fluency. It's essential. But at the same time, we value the conceptual understanding more highly. We don't want our students to only come out being able to turn the handle on problems. We want them to come out with understanding. And sort of historically, back in the 60s, I think it was, some computational science gave us this model where they managed to put computational mastery and conceptual understanding on the same axis, and that was a big breakthrough. And since then, the debate sort of hovered about, where do we put the balance point? We don't want the balance point right at computational mastery, because that would be, we don't want them only to do that, but we can't have it up at conceptual understanding. So where along this sliding scale should we put it? And I guess we want to suggest that it's not an answerable question. There is no sweet spot. Wherever you put it, it's not going to be perfect. And so we want to put out a different suggestion, which is take the line and make it into a spiral. So instead of having an end here and an end here, pick it up and turn it into a spiral, and then stack the spirals on themselves. So you do some procedural leading to some conceptual, that conceptual leads to more procedural. But then the question becomes, how do you do this in a way where students recognise what you're doing? Because if students are in this mindset where all I'm doing is learning to turn the handle, then they filter out anything else and don't hear it. Like the way they don't, that question came up, how do I get my students to appreciate mathematical history? Because it's not in the test, I don't care, it's not relevant. How do you get them out of that mindset? And we were thinking about this, and we took our inspiration for this from science. If you pick something like wet chemistry labs, being able to measure and pour an accurate measurement into a beaker, it's an essential part of chemistry. You can't do wet chemistry without it. But nobody thinks that's what chemistry is about. So we wanted to sort of suggest the analogy that this is what the computations in our maths are like. They're a necessity, but they're not what it's actually about. And so students come pre-primed with this model from science, where they go into chemistry and they do an experiment, but the purpose of it is to understand something. And in order to do that, they've got to learn a bunch of technical skills, but they're just along the way. And so what we were thinking of is, can we present maths in this sort of way and Don's handed out some things for you, which he's going to talk about, but that was the sort of thing, can we take what we're doing now, because we don't want to propose inquiry-based learning or different models of learning. We still wanted to stick with what we've got, but can we present it in such a way that it looks different and makes students think differently about it? So what you've got there is a sample case study with a traditional existing real tute sheet and our variation on it. And
so the first page that you've got is a tute sheet that was being used at university, at an anonymous university for a tutorial on, as you can see, solving solutions of linear equations, matrices, determinants, and so on. All very computational, things that we generally expect students to do. Our suggestion is really that we're still going to use the same sort of questions, but if you look at the next 2 pages, over the page and the next one, turning this around more into an experimental situation. So we have an aim of looking at solutions of equations and how does the determinant of the matrix affect the number of solutions that you have. Can you generalize these ideas? And so that's what we're working through in the rest of this sheet. And for those of you that are online, it is also, you can also get it from that location. So we'd be using much the same questions. Not all the questions are on those last 2 pages, but we'd be still using similar questions, but what we're doing is changing the focus. So rather than just, can you solve this system of linear equations? Look at these 3 systems of linear equations. How are they different? What is it that makes them different? How does that relate to the theory that we've possibly just been discussing in lectures? And how might it lead to further theory? How might you be able to generalize it? So also assuming that students are able to use software to do this, so that at the end of the day, we're asking them about something that's far more complex than they could solve by hand. But they would then be able to connect it to the theory and make sense of it. And so I think, yeah, that was just saying that. So again, we'll just finish with this quote that we started with and maybe ask if you can see that there's maybe an argument here for what we're suggesting, and invite some questions. No questions. That was thank you.
Right.
Oh, sorry. Well, it was the same as the first one.
There you go. I don't know how to make it big. I won't try. I'll break something. How about this?
Oh.
Dylan, have you changed your assessment because of the way you've approached your tutorial?
We haven't implemented this yet. This is our thinking. But we would, yes, I think assessment would also have to change. Yes.
This
Service courses, so courses that you're teaching into the faculty that you're teaching to, would you need to sort of liaise with them about?
Absolutely. I mean, I think one of the things, particularly with service teaching, is that we're being directed for what we should teach. But possibly the people who are directing us are thinking about what mathematics was like 50 years ago, not what it is today. And so we perhaps need to educate them a little more that students don't need to know 27 different techniques of integration. What they need to understand is that there are techniques out there and the software is going to be able to do it for them, and how those techniques work, rather than being able to use them all by hand.
it's something that has come out in the interviews as well. That for service teaching, it really is like that. Some random person decides what their students need to know, which is fine, but they also then articulate how it should be taught. And we're just sort of going with that. And a lot, people say, oh, I have to do it this way because I got told by such. But we're the experts. If we're not the people who are initiating the conversations and making suggestions about, well, actually, this is more relevant, this is a better way to do it, then nobody else is going to give best practice in maths ed.
Carolyn.
If you are having those conversations, I would imagine that quite a lot of people outside of maths departments and stats departments are in the group that think it's just computational. So that means you have to have someone.
There's sometimes going to have to be some hard discussions with other people. And I mean, that also means getting outside of the silo and discussing with other people about what maths is and how it should be taught today.
Sometimes you might find the students won't like it because they have to see.
Mm-hmm.
You know what I mean? And they've been indoctrinated through high school and school. I get a question, I answer it. It doesn't matter whether I understand it. But if I, you know, like tests are just, someone can get 20 out of 20. And then when you say to them, well, what did you do in this one? I don't know, I just did that on the day. And they might not like it, so it might have to be a little bit of a slow process, you know, to get them into it.
I'm sure it is going to be a slow process. And I mean, ideally, it's going to push further back down into the high schools as the way that it's taught there.
A bit more like primary level.
Yeah.
Using their techniques where they're teaching, well, so I say students, teaching students who know nothing. Whereas ours has sort of been pushed into a factory, you think this way.
Yeah, we have to break that connection. Yeah, absolutely.
So statistician. Won't say anything.
I think statisticians are further advanced with the way that we do the teaching. I mean, they're looking from the conceptual point and using the computation as a tool.
The argument you did with the interviews, and you had those 4 themes. One of the things that sort of stood out was I didn't see any theme that I could put, for example, collaboration and group work and that sort of stuff. I was going to ask for the video.
I think that fits in communication. Yeah.
Yes. Yes. So I think we may have, hopefully we put it down here. Yeah. All right. So it should be. We were just getting too short. Yes. So working with your peers and talking mathematically went into communication. Yeah.
Yeah.
The quote. The quote, the first one.
That one?
Yeah, so. Yeah, I'm not sure what I'm saying, but I'm thinking that the major problem here is if we give an impression to a young person that computers create what they expect, I think that it is a struggle to explain what's the use of technology.
Yes.
Computers don't produce themselves. I think you know, say, I was trying to explain to my students how they should try to understand the way they should use ChatGPT on all these ID stories. I'm telling them that this is a human-created database. In my understanding, a human-created database, which needs somebody who has got a very good thinking skills and all this program to design them. So when you ask a question, it's not a question which the computer answers. If the computer is programmed by someone to tell them, if this question pops up, these are the possible answers. So then, for me, that I'm trying to dispel this myth that computers can replace human beings. They're going to create solutions for us. Instead, when it's us human beings who are going to actually design these computers, make them tools.
Yeah, I completely agree with that. But our students, when we're teaching them at the moment, are just going to something like ChatGPT, take the tutorial question, get the answer back so that they can pass the exam. And you're right, we have to get them beyond that. But the struggle is how do we do that? I think we're probably out of time.
Last one. One last.
Yep.
Yeah.
Blaming it all on schools because schools are constrained by what the politicians are saying. And there is
when they design HSCs and things that are just reproducing and demanding the instruction, then it's not necessarily the teacher's fault.
No, I agree. It's not the teacher's fault. I think a lot of teachers would like to teach more this way, and it's possibly a political fight that has to be had somewhere. I mean, when I was a student and I learnt maths, I learnt it was taught in a much different way to what I see students coming through today. It depends on the state, it depends on the teacher, it depends on many things. Yeah. Thanks. Look, we'll be around for the rest of the week. So if anyone has questions or want to chat, we're happy to.